Ever wondered what makes a medium linked list question actually tough in interviews? Reorder List is a Pattern Mastery 100 favorite, regularly used at Facebook and Google to test deep understanding of pointer logic and in-place list manipulation. Over 35% of candidates get stuck or write buggy code here. Let's make sure you know how to conquer it. We'll use the basic method to systematically solve Reorder List. This approach keeps us organized, ensuring we never lose our place, literally or figuratively. Let's break it down. Given the head of a singly linked list, you need to reorder it in a very specific way. Take the first node, then the last, then the second last, and so on, alternating from both ends toward the center. Example. Input, 1 2 3 4 5. Output, 1 5 2 4 3. Real-world example. Imagine you're processing a waiting line at a theme park, but to balance both ends, you alternate pulling people from the front and the end. Or in file processing, if you want to interleave oldest and newest records for sampling, what's tricky? We must do this in place, no copying nodes or using extra lists. If you try to naively alternate pointers, you might easily lose access to the remaining nodes. Classic pattern: find the middle of the list, using fast and slow pointers. Reverse the second half. Merge the two halves, one node at a time. Think step by step. Use slow or fast pointers to split the list in half. Reverse the second half so the last node comes right after the first. Alternate merging nodes from each half, being careful with pointers, so you don't lose the next nodes in either half. Let's break it down further. After splitting, you have two sublists. First, 1 2 3. Second, reversed, 5 4. You then weave them together. 1 5 2 4 3. Edge cases, even or odd length lists, single node lists, should remain unchanged. Here's the structure. Find the middle. Use slow and fast pointers. Reverse the second half. Classic in-place reverse. See reverse linked list. Merge, halves, alternate nodes from first and second half, updating pointers carefully. Let's implement it. Set slow and fast at the head. Move slow 1 and fast 2 steps at a time until fast reaches the end. Slow now at midpoint. Reverse the second half, starting at slow. Next. The time complexity of this algorithm is O(n). We traverse the list once to store nodes, and again to reorder them, so it is linear time. Now, let's look at the idea behind this solution. We are using an array to store all nodes of the list. Here, n is the number of nodes in the list, and our goal is to reorder it like L0 lane L1 lane 1 L2. We first store all nodes in a list so we can access them by index. Then we use two pointers, I starting from the beginning, and j starting from the end. We connect nodes alternately from the front and back until the pointers meet. Think of it like lining up people from both ends of a queue and letting them shake hands alternately. If the list is empty, we do nothing. We can't reorder an empty list. Next, we create a list to store all the nodes. We also set a pointer, cur, to walk through the original list. We traverse the entire list, adding each node to the array. Now we can access any node by its position. We set two pointers, I at the start and j at the end. These will help us pick nodes from both ends alternately. While I is less than j, we first point the next of the node at I to the node at j. Then we move I forward to the next start node. If I meets j, it means we're done with the middle node. We break the loop to avoid creating a cycle. Next, we point the node at j to the next start node. Then move j backward to the next end node. This completes one round of front-back linking. The loop continues until all nodes are connected properly. Finally, we set the last nodes next to null to mark the end of the list. Otherwise, we might accidentally create a loop. So, to summarize, this algorithm first collects all nodes into a list. Then it uses two pointers to alternately connect nodes from front and back. Finally, it terminates the list properly. It is efficient, simple, and clear. We traverse the list linearly, giving O(n) time complexity. Extra space is used for the list, giving O(n) space complexity. This approach handles odd and even length lists gracefully. Before we check the output, let's understand what the problem is. We want to reorder a linked list in a specific pattern. L0 lane L1 lane 1 L2 lane 2. This test case will help us verify that the function reorder list correctly rearranges the nodes without losing any of them. Let's test our function using this input. The linked list is 1 2 3 4. We want to reorder it so that the first node is followed by the last node, then the second node, then the second to last node, and so on. Here's why the solution works. First, we traverse the list and collect all nodes into a list called nodes for easy random access. We initialize 2 pointers, I at the start and j at the end of the list. Then, we reorder the list by alternating nodes from the front and back. Nodes I next equals nodes j, links the first node to the last. Move I forward. Node is j next equals nodes I, links the last node to the second node. Move j backward. We repeat this process until I meets j, then mark the end of the list with nodes j next equals none. Step by step, the list 1 2 3 4 becomes 1 4 2 3. And that is exactly what the program outputs, 1, 4, 2, 3. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully reorders the linked list into the required pattern, efficient, accurate, and reliable. Our implementation is correct. It correctly alternates nodes from front and back. It preserves all original nodes. It marks the end of the list properly to avoid cycles or dangling pointers. The time complexity of this algorithm is O(n). We traverse the list a few times, to find the middle, reverse the second half, and merge, but each traversal is linear. Now, let's look at the idea behind this solution. We are using an in-place reorder method to rearrange the list like L0 lane L1 lane 1 L2. Here, n is the number of nodes in the list, and our goal is to reorder them without extra space. The steps are, first, find the middle of the list. Second, reverse the second half of the list. Finally, merge the two halves alternately. Think of it like folding a line of people in half, flipping the back half, and then interleaving them with the front half. If the list is empty or has only one node, there's nothing to reorder. Next, we set up 2 pointers, slow and fast, to find the middle. Slow moves 1 step at a time, while fast moves 2 steps. We move slow and fast through the list. When fast reaches the end, slow will be at the middle. We split the list into 2 halves. The first half ends at slow, and the second half starts at slow. Next, we prepare to reverse the second half. A pointer pre-way will hold the reversed list as we build it. We reverse the second half 1 node at a time. First, store the next node. Then point the current node backward to prev. Move pre forward. Move cur forward. Now, second points to the head of the reverse second half. We set first to the head of the first half. We'll use it to merge the 2 halves. To merge, we store the next nodes for both halves so we don't lose track. We link the first half node to the second half node, then link the second half node to the next node in the first half. Move both pointers forward and repeat until all nodes are merged. So, to summarize, this algorithm first finds the middle of the list. Then it reverses the second half, and finally merges the 2 halves alternately. It is efficient, in place, and elegant. We traverse the list linearly for finding the middle, reversing, and merging, giving O(n) time complexity. No extra space is used, giving O(1) space complexity. This approach works for both odd and even length lists. Now that we've implemented our solution to reorder a linked list, let's walk through how it works on a real input. We'll see how the algorithm rearranges the nodes by alternating from the start and end of the list while keeping everything connected properly. This input represents a linked list with 5 nodes. Our goal is to reorder the list so that nodes alternate from the beginning and end. First node, last node, second to last node, and so on. Here's why the solution works. First, the algorithm finds the middle of the list using the slow and fast pointer technique. Then, it splits the list into 2 halves and reverses the second half. Finally, it merges the 2 halves by alternating nodes from each half. Step by step for this input. 1 2 3 4 5 middle is at node 3, split into 1, 2, 3, and 4, 5, reverse second half, 5, 4, merge, 1 5 2 4 3, and that's exactly what the program outputs, 1, 5, 2, 4, 3. This confirms the code correctly reorders the list as intended. So, our implementation is correct. The algorithm successfully reorders a linked list in the specified pattern, precise, efficient, and reliable. Breakdown recap. Conceptually, we need to reorder a singly linked list so that nodes alternate from the start and end toward the center. It's about weaving the first node, then last, then second last, and so on, all without creating new lists. Assess recap. The tricky part is doing this in place. Naively alternating nodes can easily cause you to lose access to remaining nodes. The clean approach is threefold. Find the middle of the list, reverse the second half, and then merge the 2 halves carefully. Structure recap. Here's the plan. Use slow and fast pointers to locate the middle of the list. Reverse the second half of the list in place. Split the list at the middle and merge the two halves, alternating nodes while keeping pointer updates safe. Implement recap. We implemented slow and fast pointers to find the midpoint, reverse the second half starting from the midpoint, and then merge nodes from each half step by step. Running this on LeetCode executed smoothly without errors, fully reordering the list in place. Check recap. We verified the solution works for lists of various lengths, including edge cases like single node lists and even length lists. Time complexity is O(n), and space complexity is O(1) since no extra data structures are used. Closing insight. The key takeaway? By splitting, reversing, and merging carefully, you can reorder a list efficiently and in place. Mastering this pattern strengthens your understanding of pointer manipulation, a crucial skill for any advanced linked list problem in interviews.